What if everything you've ever believed about reality is just a shadow of something deeper? Imagine for a moment that the solid objects around you, the chair, the floor, even your own body are not truly what they seem, but only surface echoes of something hidden beneath. For over a century, physicists have been peeling back the layers of the universe, convinced they were closing in on a final theory of everything. But instead of reaching the end, they stumbled into a maze, a place where reality itself refuses to be pinned down, where space and time might not be the ultimate foundation of existence. And at the heart of that maze lies one of the boldest ideas in science, the possibility of hidden dimensions beyond the ones we can see. Think of the universe as a vast room with two windows. From one window, you see a neat, predictable world. This is the classical window, the world of everyday experience, where objects stay put unless pushed. Planets orbit stars in smooth ellipses, and the rules seem almost common sense. It's the world Isaac Newton described centuries ago, and it still guides everything from bridge building to rocket launches. But glance through the other window, and the view couldn't be more different. This is the quantum window, where certainty vanishes. Particles blink in and out of existence. They tunnel through barriers they shouldn't cross, and they seem to know when they're being watched. This world doesn't just break the rules of common sense, it rewrites them entirely. Both windows are real. Both give us truths about the universe. Yet here's the catch. They don't line up. Look through one. The universe looks smooth and solid. Look through the other. It looks jittery, ghost-like, and deeply unpredictable. The tension between these views is more than just academic, it's the deepest riddle in modern science. And it raises a chilling possibility. Maybe neither window shows the whole truth, but if these two pictures can't agree, what could possibly unite them? To find the answer, we need to look at the theory that's been both our greatest triumph and our biggest roadblock. For decades, physicists have relied on a framework called the Standard Model of Particle Physics. It's like an instruction manual for the smallest building blocks of the universe. Quarks, electrons, neutrinos, the Higgs boson, every particle we know fits neatly into its pages. With the Standard Model, scientists can predict particle behavior with jaw-dropping precision. In some cases, its predictions have been confirmed to 12 decimal places, an accuracy unmatched in any other field of science. But here's the paradox. For all its brilliance, the Standard Model is full of holes. It doesn't explain gravity, the one force that governs the motion of galaxies and the fall of an apple alike. It can't account for dark matter and dark energy, which together make up 95% of the cosmos. And it relies on a laundry list of adjustable numbers, masses, charges, couplings that have to be fine-tuned by hand, as if the universe were a cosmic machine built with mysterious dials set just right. It's like discovering a beautifully written novel where every page makes sense, but the final chapter is missing, and without it, the whole story feels incomplete. And this incompleteness becomes undeniable when we push physics to its extremes. The violent heart of a black hole, or the first flickering instants after the Big Bang. In those realms, the Standard Model collides head-on with Einstein's masterpiece, general relativity, and both begin to break down. So what happens when the two greatest theories of science can't agree? The answer may lie in the darkest, most extreme corners of the universe. If the Standard Model is our best map of the subatomic world, and general relativity is our compass for the cosmos, then black holes are where both map and compass fail. Picture a star collapsing under its own weight, crushing itself into a region so dense that not even light can escape. At the center of that black hole lies what physicists call a singularity, a point where density becomes infinite, and the known laws of physics dissolve. Now, here's the unsettling part. In order to describe what's really happening at that singularity, we'd need both quantum mechanics and general relativity to work together. But when scientists try to merge the two, the math turns chaotic. spitting out meaningless infinities. It's as if nature itself is hiding its secrets behind a wall of paradox. And it's not just black holes. Travel back in time to the very first fraction of a second after the Big Bang, and you hit the same problem. In that fiery instant, the universe was unimaginably small, hot, and dense, a quantum object wrapped in the grip of gravity. Once again, our two greatest theories collide, and both collapse under the pressure. But there's a clue. If we look closely at the sky today, we see faint ripples left over from that explosive birth. This faint afterglow, known as the cosmic microwave background, is like a photograph of the infant universe. And woven into that image are patterns, tiny fluctuations that carry the fingerprints of quantum processes mixed with gravity itself. It's our only direct glimpse into the era when the rules of physics were colliding head-on. So here's the mystery. If those fingerprints are real, then somewhere out there lies a deeper theory that can stitch quantum mechanics and gravity into one seamless picture. And for decades, physicists thought they knew what that picture might look like, until they hit a roadblock. At the heart of quantum mechanics is a simple idea. Every force comes in tiny packets, or quanta. Light is carried by photons, the electromagnetic force by them too. The strong force has gluons. So, if gravity is truly a quantum force, it must have its own particle, a ghostly messenger called the graviton. On paper, the graviton fits beautifully. It explains how gravity could ripple through the fabric of space-time, just as photons ripple through the electromagnetic field. Detecting even one graviton would be the ultimate proof that gravity really has a quantum side. But here's the catch. And it's a devastating one. To catch a single graviton, you'd need a detector so absurdly sensitive that it would collapse into a black hole under its own weight. The numbers don't just make it difficult, they make it essentially impossible. Even our most advanced observatories, like LIGO, which can register distortions in spacetime 1,000 times smaller than a proton, are still detecting collective waves made of unthinkably huge numbers of gravitons, not individual ones. It's like trying to catch a single drop of rain with your bare hands during a hurricane. You'll feel the storm, but the individual droplets are forever out of reach. This left physicists facing a sobering reality. If we can't ever catch a graviton, how could we prove quantum gravity is real? Would we be stuck forever with theories we can't test? And that's when some scientists turned to a radically different idea, one that didn't just tweak the math, but rewrote the very foundation of reality itself. What if everything you've ever known, every atom in your body, every star in the sky, isn't made of tiny point-like particles at all? Instead, imagine that at the deepest level, reality is woven from unimaginably small vibrating strings. That's the bold vision of string theory. According to this idea, particles like electrons and quarks are just different musical notes played on the same fundamental string. Pluck it one way, and you get a photon. Strike it another, and you get a graviton, the particle of gravity itself. Suddenly, the bizarre zoo of particles in the standard model looks less like chaos and more like a cosmic symphony. But the theory comes with a wild twist. For the math to work, strings can't just vibrate in the 3 dimensions we see. They need extra hidden dimensions curled up so tightly that we don't notice them. Picture an ant walking along a garden hose. From far away, the hose looks like a one-dimensional line. But up close, the ant sees it can circle around the hose's surface too. In the same way, our universe could have extra dimensions so tiny we never perceive them directly. And these dimensions aren't just theoretical decorations. They determine how strings vibrate, which in turn dictates the fundamental laws of physics. Everything from particle masses to the strengths of forces. To put it bluntly, the way the universe feels depends on the shape of these invisible dimensions. The problem? There isn't just one possible shape. There are trillions upon trillions of ways to fold those hidden dimensions, each creating a different possible universe with its own laws of nature. This vast landscape makes string theory rich, but also deeply unsettling. If every possible universe is allowed, then why do we live in this one? Still, the sheer elegance of the theory kept scientists captivated. For the first time, gravity, quantum mechanics, and the particles of the Standard Model could, in principle, be united in one framework. String theory even predicted the graviton naturally, almost as if it had been waiting there all along. For a moment, it looked like physicists had finally found the missing blueprint of reality. But just as excitement peaked, the silence of experiments began to cast a shadow. To give string theory real-world footing, physicists leaned on a powerful idea called supersymmetry, or SUSY for short. Supersymmetry proposes that every known particle has a heavier superpartner. Electrons would have selectrons, quarks would have squarks, and so on. These superpartners weren't just extras, they were essential. Without them, the equations of string theory wouldn't balance. And on top of that, supersymmetry offered answers to other puzzles, like why the Higgs boson has the mass it does, and even a potential explanation for dark matter. It was a beautiful idea, and it made a bold prediction. If supersymmetry is real, we should be able to find these superpartners in high-energy collisions. That's why, when the Large Hadron Collider, LHC, fired up beneath the French-Swiss border, many physicists were holding their breath. The LHC is the most powerful particle accelerator on Earth, smashing protons together at near light speed to recreate conditions just after the Big Bang. If SUSY particles were hiding anywhere, this was the place to find them. But here's the twist. Despite years of smashing protons and analyzing mountains of data, the LHC has yet to reveal a single superpartner. The Higgs boson showed up, just as predicted, but the rest? Silence. For many scientists, this was a gut punch. Supersymmetry wasn't ruled out completely. Some versions still survive in more exotic corners of the theory space, but the simplest, most elegant forms were slipping away, and with them, some of the experimental hope for string theory itself. Still, the story wasn't over, because just as physicists were grappling with these setbacks, a bigger, more audacious idea emerged, one that suggested strings were only part of a much larger cosmic framework. Just when it seemed string theory was collapsing under its own weight, a startling realization shook the field. Physicist Edward Witten proposed that all 5 competing versions of string theory were actually different faces of the same deeper theory, something bigger, more powerful, and stranger than anyone had expected. He called it M theory. In M theory, the tiny strings weren't the only players. There were also higher dimensional objects called branes, short for membranes. A one-dimensional string could be seen as a special case, but branes could stretch across 2, 3, or even more dimensions. Imagine vast sheets or bubbles floating in a higher dimensional space, each brane possibly containing an entire universe like ours. Suddenly, a new picture of reality emerged. Our universe might just be one 3-dimensional brane drifting in a higher dimensional ocean. Collisions between branes could even spark new Big Bangs, birthing entire universes. And if that's true, then the cosmos we see through our telescopes is just one bubble in a vast multiverse. But here's the dilemma. While the math is breathtaking, the evidence is thin. M theory lives in 11 dimensions, far beyond anything we can probe directly. Its equations hint at answers to puzzles that have haunted physics for decades, but they also leave us stranded, with no clear experimental test in sight. Some physicists believe it's the most promising path we have. Others whisper that it might be a beautiful mirage. But either way, it forces us to ask an even deeper question. What if the fundamental fabric of reality isn't made of particles or strings at all, but something even more abstract? In recent years, a strange idea has been gaining ground, one that shifts the focus from matter and energy to something more elusive: information. Think about it. Every quantum experiment shows us that the act of observation changes the outcome. A particle isn't in one place or another until it's measured. Reality, at the quantum level, seems inseparable from the observer. Some physicists have taken this to its radical conclusion. Maybe the universe itself is not a solid, objective thing, but a vast web of information that only becomes real through interaction. From this perspective, the world we see is like the interface on a computer screen, clean, colorful, and intuitive. But underneath lies the raw code, invisible yet fundamental, the hidden dimensions, the strange symmetries, the impossible math. Maybe they're not physical structures at all, but part of the informational code of reality. It's an unsettling thought. If reality is fundamentally informational, then space, time, even matter might be emergent illusions, rising out of something deeper that we barely have the language to describe. And this brings us full circle. Whether it's through strings, brains, or bits of information, physicists are chasing something beyond the windows we've always used. A new foundation that could reveal the universe for what it truly is, or remind us that every answer opens another, even stranger question. From the elegance of the standard model to the paradoxes of black holes, from the impossible dream of detecting a graviton to the bold visions of string theory and M theory, one theme echoes again and again. Our picture of reality is still incomplete. Hidden dimensions may exist, folded beyond our perception, shaping the laws of physics from the shadows. They might be the key to uniting gravity with quantum mechanics, or they might point to an entirely new way of thinking about existence itself. The truth is, we don't yet know, and that uncertainty is both frustrating and thrilling, because every time science reaches what feels like the edge of knowledge, the universe reveals another layer, another mystery. Maybe one day, experiments will glimpse signs of extra dimensions, or uncover the fingerprints of a deeper theory woven into the fabric of space-time. Or maybe the real revolution will come from an even stranger place, where information, not matter, is the true foundation of reality. Either way, the search continues. And that search doesn't just change physics, it changes us. It forces us to rethink what it means to exist, to observe, to ask questions about the nature of everything. So the next time you look around your room and see ordinary objects, the chair, the table, your own reflection in the mirror, remember this: what you see may only be the surface. Beneath it, reality could be far stranger, richer, and more multidimensional than we ever imagined. And if those hidden dimensions are real, discovering them wouldn't just change science. It would change everything.